Hi guys, good evening. Am I audible and visible?
Yeah, yes, audible and visible.
Yeah, thank you. So without any further ado, let's start today's session on sharing a screen. I hope it is visible, my screen.
Yeah, it's visible.
Yeah, thank you. So before anything, yeah. So last week I was not able to uh, conduct the session. There was some technical problem at my end. Okay, so there was some internet outage, power outage also there, so I was not able to conduct the session. So I don't worry about that. I will simply upload a video. Okay, I'll simply upload a video on the last week's content. By the way, so I'm sure all of you must have already covered the last week's content, and I mean week. I'm talking about week 10's content. So I don't think you would have a lot of problem following the content of week 10, right? Anyway, I'll be uploading a video where I'll be solving some problems on week 10's content, and there you can see. If you have any doubt, you can ask me later. So today I will not be covering week 10. I'll be covering week 11. Okay, that is the second order system. Okay, fine. So yeah, this is this is an NPTEL course. And this course name is Basic Electrical Circuits, and it is the instructor for this course is Dr. Gajendranath Chaudhary. He is a faculty member at IIT Hyderabad. Alright. My name is Mayank Anupam. I am a PhD student and a PMRF scholar. So currently I am pursuing a PhD in IIT Kanpur. Alright. So starting with this week's content. Yeah, so this in week 10 what did we see? We saw what? We saw second order system, right? In week 9 and 10 what did we see? Week 9 and 10 we saw first order circuits, right? RLC, sorry, RC or L or LR, right? RC or RL, that's all. We didn't see two different memory elements in the same circuits. So this time we have two different memory elements. So what is an inductor here and capacitor here? These are two different memory elements, right? Because they contain memory. The uh, I mean this is already something which you have seen, right? Something which you have already seen earlier, that inductor and capacitor, the voltage or the current passing through the inductor or the capacitor is dependent upon the past values, right? Past values of voltage and current. So it definitely contains it. That is why it is called a memory element, an element with memory. Whereas a resistor, on the other hand, what is the uh, characteristic equation of a resistor? So it is VR is equal to I times R, right? So the voltage at any time t across a resistor depends only on the current passing through the resistor at the same time t, right? That is why a resistor is a memoryless element, whereas capacitor and the inductor and an inductor is a element with memory. Okay, fine. So we saw second order system, and I mean this is pretty standard stuff. I mean, I mean, you must have seen this already in your class 12th also. So this is just like we know what is the how to solve a second order system, right? The differential equation which you got, and the professor also solved it for you, and we saw how to solve it, and then we got some characteristic equation, right? And based on that only I'll be solving some problems today. Okay, so the first problem is given here. In the circuit given below, okay, 1 second. Yeah, in the circuit given below, the initial conditions are I of IL, that is this current, right, is equal to 2 ampere. This is the IL of 0, which means that the current at time t is equal to 0. I mean, that is very start, right? T is equal to 0 is something is denoting the start. Okay, so initially current passing through the inductor is this 2 ampere current, right? And the voltage, initial voltage at the capacitor is 20 volts. So the voltage Vc of t for t greater than or equal to 0 is given by what? So yeah, basically they have already said that this is the equation uh, for the voltage across the capacitor at any time t. Okay, so now we have to find out all the different parameters here, like this a here, this capital A here, this capital B here, this omega here. All these things you have to find out. So how do we do that? Yes. How do we do that? First of all, what kind of a circuit is this? Is this a parallel RLC or a series RLC?
Parallel RLC.
It's a parallel
With-
RLC, right?
Yeah, without
Yes,
source.
correct. So parallel RLC, what is the this thing? Hmm, what is the equation of parallel RLC? So, one second. Parallel RLC. What is the characteristic equation? So the characteristic equation of any second order system is of the form, right? This kind, right? S square plus 2
2
zeta omega ns
omega minus
plus
plus omega n square.
is equal to 0, right? This is the characteristic equation, right? Now for a parallel RLC, what is omega n? 1 over root LC, right? Radian per second, isn't it?
Yes, sir.
And what is zeta? Or rather, tell me what is quality factor Q, and then zeta also. So another way to write this is this way, right? S square plus omega n upon 2 q, sorry, omega n upon q, right? S plus omega n square, right? This is another way to write it. So tell me what is q and what is zeta? So what is q? So tell me, for a parallel RLC, q should be proportional to 1 over r or r. What should it be? It should be r, right? Because as r increases, quality factor also increases, right? Remember something like that?
Yes, sir. Yes, sir.
Yeah. And other thing will be inside it will be c by l, right?
Right.
So what is zeta now?
Um,
So you know zeta is equal to 1 over 2q, right?
ah,
So let's it's not required here, but let's simply replace q and omega n in this equation and see what do we get. So we have s square plus omega n is what? 1 over root LC divided by q is what? R into C by L, right? Into S plus 1 over LC is equal to 0. This is the characteristic equation, right? Now let's simplify this. What will we get? S square plus this root L gone, and 1 over RC S plus, oh, pardon me, LC equal to 0, right? This is the equation which you will get for a, this is the characteristic equation which you will get for a simple RLC circuit in parallel, right? So now yeah, fine, this we got already. Now tell me, uh, when do we have this kind of a solution for that particular, so in this case, yeah, so I have written here in terms of S, right? So let's write it in terms of differential equation. So what will be the differential equation here? It will be d2 v c upon dt square, right, plus 1 over rc dvc upon dt, right, plus uh, vc upon lc, right? This is what we will have, right?
Yes.
Correct. So now tell me, for this particular equation, what will be the solution? So this kind of a solution, when do we get this kind of a solution? So it is exponential, which is like this. So it is e to the power minus some at, right? It is a minus some at times a cos of omega t plus b sine of omega t. This kind of a solution, when do we get? This is for, I mean, there are three types of systems, right? Second order system. One is over damped, one is critically damped, and the other one is under damped. So what kind
Um,
of a solution is this?
Under damped case.
Yes, it is an under damped system, right? Under damped system. So under damped systems means what? Zeta is less than?
Zeta between 0 and 1.
Yes, very good. So let's by the way verify whether this is the case or not. Whether zeta is indeed less than 1 or not here. So what is zeta, by the way? 1 over 2q, right? So what is that? Root over, so 1 over r L by c 2r, right? This is 1 over 2r root over L by c, right? This is zeta. So tell me, what is the zeta value in terms of, I mean, what is the numerical value of zeta when we put all these values here? Tell me quickly, calculate it. It is 1 over 2 into r is 5, right, into, and L is 2 Henry divided by C is 25 millihenry. So millihenry simply goes up here. This becomes what? 2000 upon 25, which is 40. So how much is this? 4 4s are 16. 16 5s are 80. So it is 4 upon 10 root 5, right? Am I correct? I think so. Yes, this is right. So is this less than 1? Is this less than 1?
Yes, sir.
Huh?
Yes, sir. Less than 1.
Yes, it is less than 1, right? I mean, if it is not obvious, just do this. Put everything inside the square root, so it is 25 sorry 16 5 is 80 divided by 100, right? So it is definitely less than 1, correct? Fine, so it is less than 1, so zeta is less than 1, so that is why this we will get this kind of a response for this system. So now let's find out all the different parameters, right? So first of all, let's calculate what will be the response of an underdamped system. So this is the general solution, right? S square plus 2 zeta omega ns. Or if you do it like this, so it is d2 vc square vc by dt square plus 2 zeta omega n into dvc by dt plus vc upon vc into omega n square is equal to 0. So yeah, so what is or let's do this, take this only here. So we have this s square plus 2 zeta omega ns plus omega n square equal to 0. So what are the solutions to this, what are the roots of this equation? S is equal to, yeah, come on, what are the roots? Right, these are the roots, right? So s is equal to how, what are the roots here? It will become zeta. So let's take omega in common as was done already in the lectures also. So it becomes minus zeta plus minus under root zeta square minus omega n, sorry, minus 1, right? These are the roots, right? Am I right? Correct. So if
Yes.
zeta is less than 1 but greater than 0, so if zeta is greater than 0 but less than 1, then what do we have? S is equal to, so this under root it will become imaginary, right?
Oh.
So it will be
1 minus zeta square.
yes, so it will be plus minus j times root over 1 minus zeta square, right? This will be the solution, right? Correct?
Yes, sir. Yes, sir.
Yes. Now just erase this, this is not required now. Fine, fine. So now tell me something, this solution here, which is of this kind, so vc of t is equal to, given that it is exponential, which is like this, e to the power minus at a cos of omega nt or cos omega t plus b sine omega t. This is the solution that we are getting here,
Okay.
right? Just tell me something, what is this a and what is this omega here?
A is minus zeta omega na.
Yes, very
A.
good. So a is basically the real part of this, right?
Okay.
So
Yeah.
what is the real part of our, so basically we have, okay, so let me write it like this. So we have P1 is equal to omega n, sorry, or rather PR, which is real, is equal to what? Minus zeta omega n, and P imaginary is equal to what? Plus minus,
Square root of
or
1 minus zeta.
let's not write plus minus, since imaginary it is, there will be complex conjugate, right? Only. So I will
Yeah.
only be taking the mod of that. So
Okay.
let's take mod of this Pi. So it is what? It is omega n times 1 minus zeta
Zeta
square,
square.
right?
Mm.
Yes. So yes. So in that case, what is A? A is simply equal to PR, right?
Yeah.
And or rather minus PR, mod of PR. Okay.
One.
And
Mm.
what is omega?
Omega is equal to omega n times of square root of 1 minus zeta square.
Mod of pi, right?
Yeah.
Correct. So that is easy, right? So now let's simply so what is mod of pr? What is a? So zeta omega n, and what is omega? So we can simply replace it, right? And now we can solve it simply. It is easy, correct? We have
Yes,
to
sir.
simply replace. So just let's replace that. So what is zeta omega n?
Zeta.
So it is here, right? Zeta omega n is what? Zeta omega n is what?
Oh.
1 over
RC.
rc,
Sorry, 1 over RC.
1 over 2 rc, right?
Yeah.
1 over 2 rc. 1 over 2 rc. What is that? 1 over
2
2 times 5. 5 is the,
into
this is
10.
5 ohm,
0. Point.
and this is 25 millifarad, right? So it is 25 milli is what? Multiplied by 1000. Is the noise bothering you? There is some noise in the background here. So is that noise bothering you?
No, no problem, sir. No problem.
Yeah,
Continue.
fine. So how much is that? Tell me. So it is, one is gone. So it is 4, right? This
Yeah.
is 4. And what will be the unit of this? What will be the unit? What will be the unit of A?
Is
What will be the unit of A? What will
real
be the unit of
for.
A here? It should be per
No, it
second,
is.
right?
Yeah.
It should be per
Also.
second. Because why? Why should it be per second? Because the argument of a exponential has to be unitless, right?
Okay.
And since there is a t here, anything which multiplies with t has to be
Okay.
opposite of I mean has to be 1 over seconds, right?
Okay.
Only
Okay.
then
Okay.
will the argument become dimensionless.
Okay. Okay.
Fine. So it is per second. Other
Okay.
yeah. So now tell me what is omega? Omega is what? Omega n
Omega
times.
is square root of 1 minus zeta square.
Yeah. So what is that?
Nothing but omega d damping frequency.
Yeah. What is that? It is oh, 1 over root LC, correct? Multiplied
Yeah.
by
Square root of
1
1
minus.
minus zeta.
So what
Zeta
is
na 1 by
zeta?
L. 1 by LC. I think.
What is zeta? You have already found out, right? Zeta
Yeah.
is 80 by 100, right?
Okay.
Tell me now. So it is 20 by 100 under root into 1 over root LC. What is 1 over root LC? How much is the value? L is 25 milli and C, sorry, L is 200 and C is 25 milli, right? So this is 25 milli and 2 Henry, right? So how much will this be?
It will
220, right?
mm,
So it becomes
20 by
400
10.
by 100, which becomes 2, right? And what will be the unit
Correct.
here of omega? 2?
Omega 2. It's frequency only, damping
Yeah, 2
frequency.
radian per second, right?
Mm, mm.
It will be 2 radian per second. That that will be the unit here. Cool. So we found omega, we have found out what is the value of A, right? These two are sorted. So A is sorted, omega is sorted. Now we have to find out A and B, right? Capital A and
Okay.
capital B. How will we find out that?
Initial conditions given
Yes, very
answer.
good. Initial conditions are given, right? So, okay, so our equation is now, let me rewrite it. So Vc of t is now e to the power minus A is what? 4t, right? And
Yeah.
capital A cos of omega is what? 2. 2t plus B sine of
Sine.
2t, right? This is our
Yeah.
equation. This is our Vc of t. It is
Okay.
given that Vc of 0 is what?
It's equal.
20 volts. It is given here. Vc of 0
Yeah.
is 20 volts. IL of 0 is
So
2 amperes. IL of 0 is 2 amperes. So let's come to that later. But first, let's find out what is VC of 0. What is VC of 0?
VC of 0 is A plus B
Equal.
is equal to A plus B equal to 20 volt.
Is it A plus B? What is
1 minute,
sine of
sorry.
2?
Sorry,
Sine of
sorry,
0?
sorry, sorry. B,
Yeah.
sine 0, 0.
Yeah. So it
A,
is simply equal to 20, right?
right, right.
So
Sorry.
A can be straight away calculated here, right? Like
Yes,
directly,
yes.
right? So
Right.
it is simply A is simply equal to 20 volts. No, no problems there.
Mm, mm.
The other thing is, it's given that the initial current through the inductor is what? It is 2 amperes. So tell me what will be the initial current through the inductor here?
Uh, B by L, 1 minute.
Yeah. How will we find out? How will we apply this condition?
No, in integrator formula you can use it.
But
L into di by dt, which is equal to V of t. From that, if I integrate, I can get it.
you say L of di by dt is
So,
equal to
sorry,
Vc.
sorry, 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 sorry. 1 minute, 1 minute, 1 minute. IL.
Yeah, so let me help you. You see,
Uh,
you already know what is the voltage here, right? What is Vc of
mm,
0? You already know that, correct?
yes. Mm.
Now, if you want to apply a condition on the initial current here, you can also
Okay,
apply by applying the KCL constraint, right? You say, you
okay.
know, if you know the voltage here, you know what is the current here, right? It is simply Vc
Mm-mm.
of 0 divided by 5. This is the current
Mm-mm.
through the resistor. Now, this
Okay,
current also, you know, this is what dVc by dt
okay.
into C, right? At time t is
Mm-mm.
equal to 0. This also you
Okay.
know. Now,
Mm-mm.
this current IL of t plus IR plus IC at time t is equal to 0, they must follow KCL, right?
Okay, okay, okay.
So IL
Total.
plus
Okay.
IR plus IC must be equal to 0, right?
Yeah.
So what is IR plus IC? This is equal to minus IL, right?
Okay.
This is correct, right now. So I simply need to find out what is the current here which is going through the capacitor at time t is equal to 0, and what is the current that is going to flow through the resistor. If I know both of them, I can equate that to IL of 0, isn't it? Which is simply given here, 2 amperes, right?
Yes, sir. Yes, sir.
Yeah, so tell me what is the current through the capacitor. So for that, what we have to do? First we have to find out what is dVc by dt, right? So current through the capacitor, which is IC, is equal to what? C dVc by dt, right? And what is that? Is equal to what?
E power minus, sorry,
So
minus
we'll have
4
to
e
do,
power minus
yes, minus 4 e to
differentiation.
the power minus 4t
A
into
cos 2t,
a
A
cos
cos
2t
2t
plus b
plus
sine
B sin 2t plus
plus,
e power
sorry,
minus 4t
e to the power minus 4t
minus 2a sin 2t, sorry,
minus 2a
7
sine 2t plus
plus
2b
2b cos 2t.
cos 2t, right? And overall this will be multiplied with c, right? This is c dvc by dt, right?
Okay,
This is the
okay.
current IC. So what is the value of this guy here at time t is equal to 0? Minus 4,
Minus
right?
4, mm,
A
minus 4a,
plus 2b, isn't it?
yes, sir.
This will go to 0 here, this will go to 0 here, correct?
Mm,
This has to be equal to and by the way, there will be a multiplication factor C here, and this has to be equal to what?
20 volt. Oh, sorry.
No, sorry, this has to be equal to nothing. This is actually IC of 0. Okay, yeah, and what is IR of 0? Simply VC of 0 divided by
Right?
R.
Mark.
Yeah, so this is VC of 0 divided by R, right?
Yeah.
IR.
VC of 0 is 12, 20 divided
Yes,
by
yes.
R
So it is 20 by 5, which
5.
is 4 amperes. Correct? And
Yes.
now simply apply KCL. Apply KCL. So what we will have? So we will have IL minus IL is equal to IR plus IC. So by the way, there will be a 0 here. IR of 0 should be equal to IR of 0 plus IC of 0. Right?
Okay.
So what is that? What is this? Minus 2, right?
Mm.
IL is 2, IL of 0 is 2, so it is minus 2 here, is equal to 4 plus IC of 0 is what? Minus 4A plus 2B into C, right? So let's replace some values here. Is minus 2 is equal to, so 4 plus minus 4, and what is the value of A? We calculated A here, right? It is 20. 20 plus 2B times C is what? 25 millifarad, correct? And that has to be equal to minus 2, isn't it? So now we'll have what? Let's put this here. Let's take this here. So it will become minus. This way. Okay, so let's do this. This becomes minus 80, and minus 80 times 25 into 10 to the power minus 3 plus 2b, this becomes 50 b times 10 to the power minus 3 is equal to minus 6. So what is this? 50b into 10 to the power minus 3 is equal to minus 6 plus, what is this? 25 into 80 is what? 2000, right? And into 10 to the power minus 3 is simply 2. So this becomes b is equal to what? This is 4 minus 4 divided by 50 into 10 to the power 3, right? How much is that? So this comes 10 to the power 2. So this is how much? 400 by 5 minus 80, right? Minus 80 volts, isn't it?
Yes.
Yeah. So now, so that solves everything, right? So we found out what is the value of A here, what is the value of B here, what is the value of omega here, what is the value of A here, right? So this was just an example to show how to do, how will you do, how will you approach these questions, right? So understood, right? Let's move on. Yeah, tell me. Again, this is a similar kind of question here. Again, we have been asked same kind of question. All the options are almost the same. What is the value of A, capital A, small a, B, C, and omega? Yeah. So there is a small difference here, right? Compared to the last one. What is that difference here in this question?
Input source voltage.
Yeah, it is a forced system, right? It is a forced system. It is now not a natural. So now the overall response should contain a term which corresponds to forced response and the term which corresponds to natural response, right? So what is this A here? By the way, so can you identify the two terms here, forced and natural?
No, A is arised due to the what kind of input you are giving to the system.
Yeah, so this is basically forced, right?
Okay.
And this is
Yeah.
what? This is
Natural.
natural, right?
Okay.
Yeah. So also tell me something. In the steady state, in the steady state in this from this equation here, tell me what is the steady state value of I of t?
Yeah.
Yeah, what is the steady state value of I of t?
6 amperes.
Huh?
6 amperes.
No, that is true. This is 6 amperes, right? Yes. But I'm asking in terms of this equation only. Tell me what will be the value of steady state current I of t?
A.
A, right? Because
A
I
alone will
of
come. E power minus infinity will become 0, so second
0,
term will
yes. So
cancel.
it will become A, right?
Okay, okay.
And that has to be equal to 6 amperes, as one of you correctly pointed out, right? So because this inductor will simply
Milliamp.
become short, right, at
Okay,
infinity, and so there will be 12 volts across this 2 kilo ohm resistor. So this is 6
okay,
milliamps, right?
okay.
So it becomes so A is directly found out, right? Now tell me what is the second term here is simply the natural response, right? So for calculating the natural response, do I need this 12 volts here? So I've already found out what is A, right? For calculating the value of A, I needed this 12 volt voltage source because A came into picture only because of this extra voltage source, right? So A is basically the manifestation of the forced nature of this circuit, right? If this voltage source was not there, if this voltage source was not present, A would not be there, right? Since this voltage source is present here, that is why we have a term here. Now I have already calculated the value of A. Now the only thing that is remaining is this quantity here, this guy here. So for that, do I need this voltage source here? Huh?
No, sir.
We
No,
don't need
that
this voltage source, right? Because
yeah,
the second term is due to the is called the
uh,
natural response, right? And natural response doesn't need a voltage source, right?
yeah. It is only due to initial conditions.
It is only due to the initial conditions, correct? Very good. So since nothing is given here, by the way, we'll assume that initial conditions are 0. Okay.
Okay.
Hmm. Now let's do that. So what do we have? If we remove this voltage source, I mean, how do I remove this voltage source? Tell me, for calculating the natural response. I have to nullify this voltage source,
Short.
right?
Short.
Yeah, short. Correct. I have to short it. So basically we'll simply short it, right? And then we'll have a resistor like this, an inductor like this, and a capacitor like this, isn't it? This is what this is
Same parallel circuit of previous problem.
correct. So now I have to find out this is IL of t, and this is VC of t. This is and this is R. This is L. This is C. Right? Yes. Tell me now. What will be the equation for this one? Characteristic equation for this one. Again the same one, right? S square plus 2 zeta omega ns plus omega n square equal to 0, right? Again, this is the characteristic equation. So tell me again, what will be the values of omega n square? Again, omega n is what? 1 over root LC, right? And what is zeta?
1 by 2 or square root of L by C.
1 by 2 r square root of L by C. Correct? Correct now? So we already saw that earlier also. And now again the same thing. What is PR here? What is PR here? Real part is minus omega and zeta, right? And what is P imaginary here? Omega n times
1 minus zeta square.
1 minus zeta square. By the way, I simply assumed here that zeta is less than 1. I assume that. Is that indeed true? I
So
mean, this happens
expression they
only
are
when
given.
zeta is, yeah, they have given the expression here, right? But you should always confirm, you should always verify this. So let's see whether
Okay,
zeta
okay.
is indeed less than 1 or not. So what is the formula for zeta? This is 1 over 2r root over L by C, right? So let's see, what is 2 into r is what? 2 kilo ohms, right? 2 kilo ohms, so it's from 10 to the power minus 3 here, right? And L is what? L is 8 millihenry. And what is C is 5 microfarad. Or this is 10 to the power minus 6 minus 10 to the power 3 rather. So how much will that be? How much will this turn out to be? 8000 by 5. How much is that? Or 1000 by 5 is how much? 200, right? So 200 into 8 is how much? 1600. This comes 40, right? 40 into 10 to the power minus 3 divided by 2 into 2, which is 10 to the power minus 2. So it is much less, right? Zeta is actually very less. Correct?
Yes, sir.
Zeta is 10 to the power minus 2. Is the calculation correct here? I mean, you verify this, whether the calculation is correct or not. I think the calculation is correct. So it is 10 to the power 3 divided by 5 is 1000 by 5 is 200. 200 into 8 is how much? 1600. And 1600 square root is 40. Yeah, so I think it's correct. Fine. So now this is, yeah, so this indeed is very less than 1. So zeta is actually less than 1. So this is correct, right? So now tell me what is the value. So from this, what is A here? A is indeed PR, right? A is PR itself. So A is PR itself. So what is AR? Or mod of PR. So what is PR? What is omega n? 1 over root LC, which is 8 into 10 to the power minus 3, and C is what? 5 into 10 to the power minus 6. How much is that? 1 over 40 into, is that correct? So it becomes 0.5 into 10 to the power minus 10 to the power 4, right? Radian per second. Oh, sorry, I made a mistake. This is omega n. So this is omega n is 0.5 10 to the power minus 10 to the power 4 radian per second. Okay, and what is zeta? We have already seen. Zeta is 10 to the power minus 2. So what is PR? Mod of PR, which is equal to A, is equal to 0.5 into 10 to the power 4 into 10 to the power minus 2, right? Is equal to 0.5 into 10 to the power 2, right? Is that correct? Is this correct?
Yes, sir, 50.
Yeah. So it is 50. And what is it? 50 per second, right? isn't it? So it is 50. Actually, it is radian per second. Actually, all right. So we got the value of A. It is 50 radian per second, right? Also, we found the value of omega. So yeah. So now tell me what is the value of omega here? What is omega here?
Omega n square root of 1 minus zeta square.
Omega minus zeta square. So since this zeta square, this zeta is 10 to the power minus 2, zeta square is 10 to the power minus 4, right? So this is like extremely less than 1, right? So I can simply ignore this. Simply ignore this. Doesn't matter. So it will simply be equal to omega in itself. So omega n is what? Is equal to 5000 radian per second, right? So omega is also equal to 5000 radian per second only, right? Now tell me what are the values. So yeah, A we already found out 6 milliamperes. Tell me what will be the value of B and C. So what is the initial current here? Since nothing is given, what do we assume? The initial current is what? Yeah, so since nothing is given here, I simply assume that
0.
IL of 0 is 0, right? Also we assume that VC of 0 is 0.
Okay.
Okay. So yeah, if IL is 0, then what is the value of B and C? So what is IL of 0 here? A plus B, right? This has to be equal to 0. So what is B equal to? Minus A, right?
Okay. Minus
This is equal to minus 6 milliamperes. So it should be minus 6 milliamperes. And C again you have to find out in the same manner as we did earlier. For that,
Okay.
what do we do? You know that the current here is current here, right? So you simply write L di by dt here,
Okay.
which is the voltage across this, and that has to be equal to this, right?
Oh, sure.
Right?
Parallel voltage system.
Yeah. So parallel voltage is actually equal to same, right? So the voltage L di by dt is equal to Vc, right?
Okay.
At t is equal to 0 has to be equal to Vc of 0.
Okay.
When you do that, you will find another constraint. From there, we can find out what is the value of C. Okay.
Yes, sir. Yes, understood.
Yeah. So I guess this takes care of this problem also. I'm sure all of you must have understood.
Yeah.
Yeah.
It's clear.
In the previous question, you have taken A as per second. Now you have taken radians per second.
I couldn't quite hear you. Please, could you please speak up?
In the previous question, you have taken A
Yeah.
as a per second. Sir.
Oh yeah.
A
Actually, it
value.
is radian per second. So radian is actually unitless. Okay, I mean dimensionless. So that is why per second seconds doesn't matter. But yeah, it should actually be radian per second. Okay,
Okay, sir.
fine. Yeah. So let's come to question number 3. In the given circuit below, the value of R equal to make the response V0 of t over time, the damping factor of 2 will be equal to what? Yeah, so tell me what kind of a circuit is this? I mean, is it parallel RLC or series RLC?
Parallel.
How do you say that?
Open the input.
You see, always, when you try to find out the nature of a RLC circuit, whether it is parallel or a series, first you have to nullify all the sources. Okay, all the independent sources. First you nullify them. So in this case, this current source here, you nullify it. How will you nullify this current source here? You open it, right?
Open it.
Yes, and after that you see that the circuit here is actually, parallel RLC, right?
Yeah.
Yes. So from that, now tell me what is the now since I have solved so many equations, you must be now you can directly say what is the damping factor here, zeta. What is that? It is 1 over 2R root over L by C, right?
Yes.
How much
Yeah.
is that? One over, what is 2R? 2 into 10, right? Root over L. L is what? 0.5, sorry, 20 Henry. 20 Henry divided by C is 0.5 into 10 to the power minus 9, right? Correct? So tell me what is this? 1 over 20 into 20, 200 divided by 5, which is equal to how much? 40 into 10 to the power 9 minus 9. So it becomes 4 into the power minus 8. 2 by 20 into 10 to the power minus, oh sorry, rather it is 10 to the power plus 8. Is this correct?
Sir, it's
This is
10,
not correct. This is not
10K.
correct. 40 into 10 to the power 9, right? So it becomes 24 into the power 10, right? Now is it correct? It's 2 into 10 to the power 5, right? So how much is that? 10 to the power 4, isn't it?
Over damped system.
Yeah, it is over damped. So I mean, this question is asked. The question here is that you want to make the system over damped with a damping factor of 2. Since right now the damping factor is very large, right? 10 to the power 4, but we only want a damping factor of 2. So what should I do? What should be the value of? I mean, what should I do? Tell me. If you only want to change the R, this resistor R, what should I do? Right now the damping factor is very large. You want to reduce the damping factor to 2, right? So tell me, what should I do to the
Okay.
R, this R here? Should I increase it? Should I reduce it?
No, it is indirectly professional.
Yes,
Or
or
so.
not indirectly
You
proportional.
have to increase.
The correct term is inversely proportional. Okay.
Sorry.
Yeah, yeah. So tell me,
You
what
have to
should I do?
increase.
I should.
Yes,
Increase.
increase.
If you increase R, then what happens? This zeta
Yes.
factor goes down, right?
Yes.
So tell me, how much should I increase? I mean, I need to make it to 2. Have I done a calculation mistake somewhere?
I have a doubt. This much. It's, Zeta normally not will come in terms of 10,000 or 1,000 just like that.
No, no, it can come. That depends upon the values. So tell me, have I done a mistake somewhere in
No,
terms of
sir. Correct,
calculation?
sir. No, sir.
Check it out from
It's
It is 2 into R is 10. So this is root of L by C.
it's 10,000 only, sir.
You have cross checked, right? You cross checked it.
Yes, sir. Sir.
Yeah. So something is wrong here. Zeta has to be reduced. Over damping. 40 factors of reduction material.
it's correct only. It is in entry.
Yes.
So
So
correct.
yeah. So options here are wrong. Anyway, so tell me what will happen. How will I make it equal to 2 here? So zeta has to be what? 1 over 2r root over L by C has to be equal to 2. So R has to be equal to 1 over 4 root over L by C, which is how much? 4 into 2 into 10 to the power 5, right?
Mm.
Correct? So how much is that? It's equal to 5 into 10 to the power 4, or rather 50 kilo ohms. Correct?
Okay. Mm.
Yes. Something is wrong here. Something is wrong here.
No,
It's
if
fine.
inductor is micro ohms, then only you can get very
Yeah.
less.
If inductor is in, the inductor value is actually not actually correct. So
Micro
yeah,
ampere.
something is wrong with the question.
Problem.
Okay.
No, no problem.
So this option is actually not correct. Okay. So ignore these options here. The correct answer is this only. Okay. Fine. Fine. So let's move on. Yes. The second order system in the circuit shown below is governed by the following differential equation. This is the differential equation which governs this second order system here. Okay. Yes. So tell me what is the value of this guy here, zeta here. Again the same thing, right? This is again the same thing. You already know. Correct. So what is zeta here?
1 by 2 or square root of L by C.
What is that?
10, 20.
L is 20 by C is 0.5 nanohenry nanofarad, which is over 9. That's quite large. Hmm. 1 over 20. I guess it is the same, exactly the same, right? As
Yes, sir, same.
oh yes, it is exactly same. So it is 10 to the power 4, right?
Yes.
No need to even solve it. So it's 10 to the power 4. Value of omega n in mega radian per second. This guy here. What is that? Root over LC, right?
Yeah, 1 over root L C.
Is equal to what? 1 over root over 20 into 0.5 10 to the power minus 9. Correct? How much is
Okay.
that? So it is 10, right? 10 into 10 to the power
10.
minus 9, which is 10 to the power 4.
Mm.
No, no, no. Sorry, something is.
No, 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 sir.
Yeah, it is right. Right. It is right.
10 for 10.
It is correct. 10 to the power 4. Yes. So how much is in terms of mega radian? So this is radian per second.
Okay.
So how much is that? 0.01
0.01
mega
into
radian,
10 to the power. Okay.
right? 0.01. Value of quality factor Q. What is Q? 1 over
R into square root of C by L.
R into square root of C by L. Very good. So what is that? Oh, let's write here. Q is actually equal to R into square root of C by L. What is that? R is 10, C is 0.5 to the power minus 9 divided by what is L? L is 2, right? 20 Henry. Yes, this will be how much? 10 into 5 into 10 power minus 10 20. So this is actually 10 power minus 11. Correct? So 2.5. So yeah, something it will be something. So don't bother. Don't bother calculating it. It will be very small, right? The quality factor is actually very small, isn't it? Isn't it? See, the quality factor is very small.
Yes, sir.
Now tell me, what is this type of the system? Critically damped, over damped, under damped?
Overdamped. Zeta is greater than 1.
Yes, it is extremely overdamped. It is highly overdamped. Zeta is very large, very large, right? Zeta is extremely greater than 1 here. It is overdamped, severely overdamped. Okay, fine. So what is the next question? Yeah, finally something to play with, series RLC. Yes, so tell me what is the, again for series RLC also. So by the way, this is a series RLC. Are you able to identify? This is series RLC, right? You must be able to identify this. You simply have to nullify this voltage source here, and then you will see that the overall circuit is like this, right? It's a simple series RLC here. Okay. Now tell me, for series RLC, again the equation is same, right? So it is s square plus 2 zeta omega ns plus omega n square equal to 0, right? What is omega n here? 1 over root LC. What is zeta here? Or rather, tell me what is the quality factor. So this is square plus omega n upon q s plus omega n square equal to 0. Oh, I think I made a mistake somewhere. Is it omega upon n upon 2q or it is omega n upon q? What is it? What should it be? Omega n upon q or omega n upon 2q? Do you remember? So actually I also forgot. What is it, by the way? Can someone please look up and tell me whether it is omega n upon q or omega n upon 2q? Yes, q is equal to upon 1 upon 2 zeta. Is it correct or not?
Yes, 2 zeta, sorry.
Huh?
2 zeta. 2 zeta. 1 divided by 2 zeta.
So this is right, right?
Yeah.
So this is also right in that case. It's omega n upon q. Okay,
Mm.
fine. Moving on. So tell me. So yeah, omega n is equal to 1 over root LC. So what is q for a series RLC? 1 over r and then c upon l, right?
Mm.
No, sorry. L upon c. Is it correct?
1 minute.
I think it is correct.
Mm.
Okay. Yeah. So tell me. Yes. Now tell me what is the. So what is zeta here? 1 over 2q, right? 1 over 2q, right?
Yeah, 1 or 2 q.
So what is that? 1 over 2 into, so r over 2 into c upon l, right?
Mm.
So what is that? Tell me for this particular question, what is zeta? R is how much? 10 upon 2 root over c is what? 10 picofarad. What is L? L is 1 nanofarad. Correct? It's minus 3, right? 10 to the power minus 2, so it will become how much? 10 to the power minus 1, so it is 1 over 2, 0.5, right? So it is actually 0.5. Again, tell me what is omega n? 1 over root LC, correct? How much is that? 1 over root L is what? 10 to the power minus 9. And what is C? C is 10 power minus 12. How much is that? 10 to the power 10, right? This is 10 gigaradian per second. Correct? Are you guys able to follow me? So
Yes,
you
sir.
should
Yes,
also
sir.
solve at your end. So I may make some mistakes, so be able to catch me. Yeah, tell me what is the quality factor Q here? What is quality factor here? One over 2 zeta. How much is that? 1, right? It is 1. Yeah, what is the type of the system?
Underdamped.
Yes, it is underdamped. It is underdamped, right? By the way, I mean, is this correct or not? Q is equal to 1 over 2 zeta. Is this correct or not?
Correct only,
Have
sir.
you,
It is.
have you verified? I mean, at your end?
Yes.
You have verified it, right?
Verified, sir. Formula verified.
Yes, good. Fine, so this is clear, right? And I have another question also here, but this is pretty much the same. The voltage of parallel RLC given by this equation here. So this is the equation of parallel RLC here. Okay, and we just have to find out. Yeah, you have to find out the value of C required to make the response over damped with a damping factor of 2. Yeah, so tell me. So if you replace it here with this, so you simply take C common here. So it will become d2V by dt square plus 1 over RC dV upon dt plus 1 over LC V of t or V equal to 0. So what is omega n is equal to 1 over root LC, and what is Q here? This is actually omega n upon Q is equal to 1 over RC. So 1 over LC root LC divided by Q, or rather RC is equal to Q. So what is this? R goes on top, right? And then this becomes what? Towards C by L, right? Fine. So
That's correct.
I simply verified the earlier formulas, the one that was causing confusion for me. So I simply verified it. So it is how much? Root over C by L. So the question that okay, but by the way, so zeta is what? 1 over 2 R L by C, right? So the question that is asked to you is, you want to make the system over damped, okay? You want to make the system over damped with a damping factor of 2. So for that, how much value of capacitance should you choose? What is the value of capacitance that you should choose? Tell me. So E has to be equal to 2, right? And what is 2R? R is 8. L is given to you, which is 62.5 10 to the power minus 3 divided by C is equal to 2. Yeah. Tell me, what is the value of C here? So it is 16 to the 32, right? Or 16 to the 32. So 62.5 into the power minus 3 divided by C is equal to 32 square. 32 into 32. So from here C is equal to what? 62.5 into 10 to the power minus 3 divided by 32 into 32. So you may as well solve it. I mean, I'm not going to solve it. You will get some answer here. So this is very straightforward now. Are you able to understand what I'm doing?
Yes, sir. Yes, sir.
Yeah, so this is pretty straightforward. I mean, there's nothing much to be done here. So this is a tricky question here. So the question here is that consider the circuit shown below. The capacitor has an initial voltage and the inductor has an initial current. So which type of response is exhibited by the circuit? And the options are critically damped, overdamped, underdamped, undamped. So you have been given that this capacitor has some initial voltage, okay, and the inductor has some initial current also. This IL of 0 is not equal to 0 and VC of 0 is also not equal to 0. In that situation, the question that has been asked to you is which type of response is exhibited by the circuit. So tell me the nature of the response, the nature being critically overdamped or underdamped. This nature, is it dependent upon the initial condition?
No, sir.
Right?
Depends
It is
on the
not.
elements in the circuit.
Yes, correct. It only depends upon the elements which are making up the circuit, right? So tell me, how will you verify whether this is critically underdamped or overdamped? You will simply do that by
Zeta.
finding
Zeta.
zeta, right? So what is zeta?
1 by 2R into L by C. Root over L by C.
Yes, right. So what is that here? 1 by 2 into 10 root over L is how much? 100 divided by 1 by 20. So it is 20 here. Correct. So is this less than 1, greater than 1? How much? So it is 1 over root 20, right? It is 1 over root 20, right? So it is definitely less than 1. So what kind of system is this? Yes, what kind of system is this? Is this underdamped, right?
Yes,
Between
sir.
0 and 1 zeta.
Yeah, so it is underdamped, correct? It is underdamped. So this was quite quick. So I only had this many questions today to discuss. This was quite quick. Do you have anything else you want to ask me?
Sir, explain about power factor, sir.
What factor?
Power factor. Q. Power
Quality
factor.
factor.
Q. Q.
I couldn't hear you. Can you please speak up?
Q, sir. About Q. Power factor.
Oh, Q. You see, Q is actually the derivation of Q is actually energy stored by energy dissipated. This is what is Q. Okay. This is how Q is defined. The quality factor is defined. So you see, this quality factor derivation is actually like at some frequency omega. This is how it is at some frequency omega. So at any frequency omega, you want to find out how much is the energy stored by the system, okay, and how much is how much is the energy being dissipated at this at that frequency, okay, and based on that you have to find out, you calculate what is the quality factor by using this relationship here. So exact the derivation here is out of the scope of this particular this particular course. So you will be learning that later in some higher level RF course. You will be definitely learning these things, but so broadly speaking, this is the this is the this thing this is the definition of quality factor, okay. So quality factor also, so basically you see from this definition here, you can clearly understand that it is a measure, quality factor is a measure of how good your circuit is in terms of storing the energy, okay. Are you following me? I mean, you see,
Yes,
if
sir.
the energy dissipated is 0, then the
Okay.
quality factor becomes infinity, right? So if your quality factor is high, which means that the quality of the circuit is high in terms of storing the energy that it has, okay, it will not dissipate that energy. So high quality factor means the energy is stored in the circuit. If you give some energy to it, it will simply store that, it will never dissipate it, okay. That is what infinity quality factor means. If the quality factor goes down, it means that the energy that is being stored by the that is being given to the system is being dissipated by the system, okay. And if the quality factor is very low, okay, it means that the energy is being dissipated very fast, very soon, okay. Whatever energy you are giving to the system, that is being dissipated very fast. You understand?
Yes, sir.
Yes, that is how that is what it means to be, what that is what is the meaning of quality factor. So that is why in a parallel RLC, you see, if the R becomes infinity, if this R here, it becomes very large, it means what? It simply becomes open circuit, right? It becomes very large, then there is only C and L in this circuit, and you know that. And LC circuit is what? It is a resonator, right? It never dissipates any energy. Whatever energy you give to it, it will simply store that. It will never dissipate it, right? So that is why quality factor for a parallel RLC is dependent, is directly proportional, right? So Q for a parallel RLC is what? R into C by L, right? Whereas for a series circuit, you want to make sure that the R should be as low as possible, right? If R is very low, then for a series circuit, there is again only L and C. From there you can see that again the quality factor becomes infinity there also. So do you understand what I was trying to say?
Sir.
Yes, sir. Understood.
Yes. So
Sir,
please understand that this is the scope of this particular thing, the derivation of quality factor in terms of this particular definition here. It is out of the scope of this particular this thing course. It will definitely be taught to you when you do some higher level RF courses. Okay, RF microelectronics, such kind of courses if you do, you will definitely learn this. Okay,
in first order circuits also we will see Q, sir. First order
come again.
circuits. In
First
first
order
order
circuits also.
circuits, we don't come across Q, sir, in problems.
I
We will
couldn't
find
hear
there
you.
also. We will find Q factor also in first order circuits, sir.
Q factor in first order
We,
circuits.
yes, sir.
You
Do
can
you
define
find?
it. You can define it. Do not use it. I mean, quality factor only comes into picture when you want to characterize a. I mean, you see, energy is stored in the system only when there is a. You see, there is RLC. There is L and C here, right? You see, this guy L and C. This is a resonator, right? The job of an LC oscillator is to simply store energy, and the this thing the quality factor here is to it simply quantifies how good that LC resonator is, right? So you do not want to talk about quality factor in a first order circuit because you know that it will always dissipate, right? You understand? For a first order circuit, it will always dissipate the energy, right?
Yes, sir.
It can never become an ideal oscillator, right? So
Yes, sir.
quality factor is a measure of how good a resonator is, and that is why it is like it's only um, we define it only for second order systems. Okay. All right. So if that is all, maybe we can meet again next time. So please
Sir,
note
while
that.
you are putting the video for last week,
Uh-huh.
on app based problem is there. App based circuit for a differential equation.
Op amp based.
Yeah, yeah.
Okay, I will see.
You see
Which
that
question?
you just solve one type of problem on that because we don't have any material regarding that.
Oh, all right. Okay, sure.
You just go through it, sir. Go through it and just put one problem on it. Enough.
So this is op amp based problem is there in this week in week 10's.
It is in previous week.
Okay, okay. Assignment you are saying previous week assignment. All right, I will put a question there based
Okay.
on that. So please note that the next session that is on next Saturday, it will be final session. Okay,
Okay.
last session for this course.
Okay.
That will be quite long. Okay, it will be approximately 2.5 hours, maybe 3 hours
Okay.
also.
Okay. Okay.
So I'll be
Okay.
simply summarizing everything that we have learned so far. I'll be solving
Sure.
the questions from the
Sure.
start till end. Okay, some
Okay.
questions, sample questions. So
Okay.
please be prepared. Okay.
Sure, sir. Sure. Sure.
Sir, your week 10 live session recording is not uploaded yet,
Yeah,
sir.
yeah, yeah, yeah. I know. Because I there were some technical problems at my end, so I could not record anything. I mean, I could not conduct the session also on that day. I will put a recording. Okay, I'll put a recording on my YouTube.
Okay, sir.
Okay, and so if I'm not able to put a recording, definitely in the next class I will. Since the next class is going to be the final class, I'll cover all the concepts. Okay, so don't worry about it. I'll
Okay, sir.
cover all the concepts from the start till end. I'll be asking your doubts. You can ask me
Sure,
anything
sir.
that you want and anything that you want from the
Sure.
start till
Sure.
end.
Sure. Thank
Okay.
you.
Yeah.
Okay, sir. Thank you, sir.
Mhm. Okay.